Okay, so when we last left off, we discussed carbonyl substitution reactions and reactions to prepare esters and amides directly from acyl chlorides. When we talked about these acetylation, esterification, and aminolysis reactions last class session, we noted that depending on the steric and electronic character of our alcohol, we can get selective reaction of one of our alcohols in our molecule. So looking at the following example, we have a tertiary alcohol and a secondary alcohol. And as we discussed last class session, in general, which alcohol reacts first? The more hindered tertiary alcohol or the less hindered secondary alcohol? Which alcohol is more reactive? What does the class think? Let's try to get some responses. The less hindered. And which alcohol is less hindered, the tertiary or secondary? The secondary, exactly right, exactly right. Okay, so with that established, let's take a look at the following example and let's refresh our understanding of the mechanism for alcoholysis and ester formation from an alcohol and an acyl chloride. So we have our alcohol, we have our acyl chloride, which in this case is acetyl chloride, and we have pyridine, which is a organic non-nucleophilic base. And what I'd like us to do, just to refresh what we've talked about last class session, is to try to predict the product from this reaction. And I'd like students to volunteer drawing a mechanism for this reaction. So let's work on this problem for about 3 to 4 minutes. And then I'd like students to share their responses in the chat, verbally, and ideally annotated directly onto the course whiteboard. So, as we work through this example, would anyone like to volunteer and try annotating out a mechanism for this reaction? So we have an alcohol. We established that this secondary alcohol is less hindered and more reactive. And we have an acyl chloride. Let's try to draw a textbook carbonyl substitution mechanism. You can also verbally explain the steps in the mechanism or share a photo of your written work in the chat, and I'd be happy to transcribe it onto the class whiteboard. So this is a good refresher example just to get us back in the rhythm of drawing mechanisms for these carbonyl substitution reactions. So we have a student that shared one of their mechanisms in the chat, and another student is beginning to annotate their mechanism. So I will check both of them. So the student proposed mechanism that was shared in the chat looks reasonable, and in fact closely matches the drawn mechanism that one of our students is annotating onto the class whiteboard. Okay, so in this case, we have an alcohol and an acyl chloride. Our alcohol attacks the electrophilic carbonyl carbon. We get a tetrahedral intermediate. And now when this tetrahedral intermediate collapses, we kick out our leaving group, which in this case is chloride. From here, we now have this protonated ester. And to get our neutral isolable product, our organic base, which in this case is pyridine, is going to pull off our proton. Perfect. So this proposed and drawn mechanism that the student's sharing on our class whiteboard perfectly matches other mechanisms that were shared in the chat as photos by students in the class. So we see some great class consensus in terms of the mechanism for this alcoholysis reaction. So what I'm going to do is I'm going to clear the annotations and then redraw this mechanism on the class whiteboard. So in this case, we have our tertiary alcohol and a secondary alcohol. The secondary alcohol is less hindered and thus substantially more reactive. So the first thing that's going to happen, we have a nucleophilic alcohol. It will attack the electrophilic carbonyl carbon, and that in turn will give us a tetrahedral intermediate. One thing that I appreciate in this proposed mechanism is that the student didn't go to immediately deprotonate the alcohol. We're under mildly basic conditions, but as we discussed previously, we won't really see a lot of the alkoxide species in solution. From here, this tetrahedral intermediate will collapse and will kick out our leaving group, which in this case is chloride. From here, we get our protonated ester, which can then be deprotonated with an equivalent of pyridine. So based on the mechanism for this reaction, would we need stoichiometric or catalytic pyridine? Do we need one equivalent of pyridine or can half an equivalent suffice? What do we think for this mechanism? Would we need stoichiometric or catalytic base? Considering the steps drawn out for this mechanism. So looking at the deprotonation step, pyridine is soaking a proton. For each equivalent of ester we generate one equivalent of H+, right? So then if we want this reaction to go efficiently, would we need stoichiometric or catalytic pyridine? Stoichiometric, exactly right. It's always important to think about what's going on mechanistically because it directly tells you how to design your reaction to get effective throughput. If you use less than one equivalent of pyridine, the reaction may be a little bit slower because that deprotonation step isn't occurring as readily. Any other questions on this example? So if you wanted to go through a formal alkoxide intermediate, then you'd use a strong base with a conjugate acid pK of greater than 3, different from the alcohol. So you can use something like sodium hydride. You could use something like even tert-butoxide would be equilibrating. You can use LDA, any sufficiently basic species that's enough to pull off that proton. Since it's mildly basic, you don't see a lot of the alkoxide generated, so it's slightly more correct to draw the pyridine just serving as a base to pull off the proton from this acidic protonated ester. So pyridine is scrounging off a proton, but it's not deprotonating the alcohol directly because the pKa difference isn't sufficient. Okay, let's keep going then. So we've seen an example of an alcoholysis reaction. Let's talk about an aminolysis reaction. So in this case, we are preparing an amide from acetyl chloride and ethylamine with triethylamine as our base. So before we get into drawing the mechanism, I just want us to think a little bit for a moment, and I have the following question. First, why is triethylamine okay to use as a base in this case? Why do we not see reaction of triethylamine with our acetyl chloride? What is unique about triethylamine that makes it a poor nucleophile for this kind of aminolysis reaction? What's special about triethylamine? When we talked about aminolysis reactions, we can make a range of amides, free, primary, and secondary. The highly substituted amides are more difficult to prepare. Triethylamine is a tertiary amine, right? It's bulky, yeah, that makes it a poor nucleophile. But the second and really important reason is if we think about the amide that we generate, in this case, we have, rather than a formal amide, we have this ammonium-like leaving group. And this leaving group can be readily lost when any even remotely strong nucleophile attacks our carbonyl. This amide, where we have complete substitution of our nitrogen, and we have this quaternary nitrogen, is not stable. And as a result, triethylamine won't interfere in this aminolysis reaction, because even if it did react, you generate a species that's so unstable, it'll just decompose back to the reactant. So you can prepare a range of substituted amides, but you cannot use a tertiary amine because the resulting amide is not stable. You have a great leaving group, and that leaving group will be lost in the presence of any other nucleophile. Does that idea make sense to everyone? Does that discussion make sense? Okay, so now let's try to apply what we've learned, and let's try to predict the product from the following reaction and draw a mechanism for the following reaction. So we have one student drawing the first step in this mechanism, which is attack of our nucleophile onto the electrophilic carbonyl carbon. We have a tetrahedral intermediate, and we have such a wonderful leaving group in the form of chloride. So we can kick out this wonderful leaving group and make our amide. Now, we just need to clean up this product and pull off our proton to get our neutral isolable amide. And in that case, our base, which is triethylamine, will pull off a proton from our amide nitrogen to generate our neutral isolable amide product. Yep, and this student proposed mechanism looks completely reasonable. The triethylamine is not incorporated in the product. It just pulls off a proton. So based on the mechanism drawn, we break our nitrogen-hydrogen bond, and that gives us a lone pair on nitrogen. Yep, exactly right. So we have this ethylamine-derived amide. Yep. And the student proposed mechanism looks completely reasonable. So let me clear this student drawn mechanism and let's redraw this mechanism on the class whiteboard for our instructor key. So the first step in this mechanism is a nucleophilic attack on our electrophilic carbonyl carbon. From here, we get a tetrahedral intermediate. That in turn will collapse to kick out our great leaving group, which is chloride. From here, triethylamine will pull off a proton from our amide nitrogen, and that generates our neutral isolable final product. Any questions on this mechanism? Any questions on alcoholysis and aminolysis? Okay, so let's keep going on then. And let's talk about further reactions of these acid chlorides. You can directly convert an acid chloride to an alcohol via reduction with lithium aluminum hydride. This occurs via a successive reduction, first to yield an aldehyde, and then the resulting aldehyde generated is reduced a second time to generate the corresponding alcohol. This mechanism closely mirrors the reduction of esters. So hydride attacks, we generate a tetrahedral intermediate. This time we have a great leaving group in the form of chloride, and we get an aldehyde intermediate. Under lithium aluminum hydride reduction conditions, you're never able to fully isolate the aldehyde generated. The aldehyde will almost immediately react via a second reduction reaction to generate the corresponding alcohol. Generally, it's preferable to go through an ester rather than directly reducing an acyl chloride, because typically this reaction is quite vigorous as you have a very strong electrophile reacting with a very strong nucleophilic reducing agent. So, treatment of acyl chlorides with lithium aluminum hydride gives the corresponding alcohol. Does this mechanism make sense to everyone? Are there any questions on this mechanism? Okay, so let's keep going then. Interestingly, you can also generate alcohols directly from carboxylic acids via reduction with lithium aluminum hydride. One thing to note is that the aluminum isn't just simply serving, it's not just It doesn't just have a bond to a hydride equivalent. The aluminum can also coordinate and function as a Lewis acid. So, lithium aluminum hydride reductions of carboxylic acids, the first step is that hydride is going to remove a proton. From here, hydride will then attack the electrophilic carbonyl carbon. And this is where aluminum really plays its critical role. Aluminum helps coordinate the anionic oxygen atoms, and it can help facilitate loss of our oxygen atom leaving group. Because rather than losing a hydroxide or O2 minus equivalent, instead, this oxygen atom is coordinated to aluminum and activated as a leaving group. Does this idea of Lewis acid activation make sense to everyone? So aluminum coordinates our oxygen atom, and that activates the oxygen atom as a leaving group. If we didn't have this aluminum Lewis acid floating around in solution, this collapse of our tetrahedral intermediate would be far less efficient. Any questions on that statement? Similar to how in the Friedel-Crafts reaction, aluminum activates the halogen as a leaving group. It's also part of the reason why these reductions are so efficient, because aluminum is also partially coordinating your carbonyl. Now, once we have this aldehyde, the aldehyde's not going to stick around for very long. A second equivalent of hydride will swoop in and attack the electrophilic carbonyl carbon, and that gives us our desired alkoxide ion, which can be protonated to give an alcohol. Does this mechanism make sense to everyone? Okay, so let's keep going now. And this is a really important subtheme. And this is reactions of acid chlorides with organometallic reagents. Grignard reagents react with acid chlorides to yield tertiary alcohols in which two of the substituents are the same. Think of an acid chloride as similar in reactivity to an ester. Mechanistically, this occurs via a series of stepwise additions, where we have a carbonyl substitution to replace our chloride leaving group, followed by a 1,2 addition to give our alcohol. I'll draw the mechanism for this reaction below. So we have our acyl chloride, and in this case we have methyl magnesium bromide or methyl Grignard. So in this case, methyl Grignard, I'm going to draw it as a carbon-centered anion, will attack our electrophilic carbonyl carbon. From here, we get a tetrahedral intermediate. And this time we do have a reasonably competent leaving group, so we'll kick out chloride. From here, although we generate a ketone, this ketone is not isolable. And this ketone will readily react with a second equivalent of Grignard to generate the corresponding alkoxide ion. From here, you can protonate your generated alkoxide ion, and that gives us our desired alcohol. Does this mechanism make sense? Reactions of acid chlorides or acyl chlorides with Grignard reagents? Okay, so let's keep going then. Let's try to apply what we've learned to the following examples. So in this case, we're asked to predict the product of the following reaction and draw a mechanism for this reaction. So in this case, we have an acyl chloride and we're treating it with lithium aluminum hydride in ether. So let's take about 3 to 4 minutes and work through this example. Let's try to predict the product from this reaction and draw a mechanism for this reaction. And of course, don't be shy to share your proposed responses in the chat, verbally, or anically onto the class whiteboard. And if there are any questions, don't be shy to ask them in the chat or verbally, and I'd be happy to provide my input and feedback. So we already have students starting to draw the mechanism. One thing I would note, we're not using methyl Grignard in this case. In this case, our nucleophile is hydride. Same theme, but it's always important that we draw the correct nucleophile. So lithium aluminum hydride is a hydride donor, so it donates an equivalent of hydride or H minus. Yep, exactly right. So hydride attacks the electrophilic acyl chloride carbonyl carbon. From here, we get a tetrahedral intermediate. And in this case, the tetrahedral intermediate collapses to kick out our leaving group. And our best leaving group is chloride. However, the aldehyde that we make is not going to last very long under the reaction conditions. And as we've seen time and time again in previous chapters, aldehydes react readily with nucleophiles. And in this case, we still have extra equivalents of hydride floating around. So our nucleophilic hydride equivalent will attack the electrophilic carbonyl carbon. From here, this gives us a tertiary alkoxide ion. Would you be able to redraw that structure just to clearly show the carbonyl carbon after the reduction? So mechanistically, you've shown that we're forming a bond. It may be easier just to redraw that base carbon atom. Yeah, exactly right. So we have our tertiary, well, in this case, we have our alkoxide ion, and we've donated 2 equivalents of hydride. So in this case, it would be primary. Yep, this student proposed mechanism looks completely reasonable. So let me just clear those annotations and let me redraw this mechanism. So that way we have an instructor key when we export this note set. So we have our acyl chloride, our hydride equivalent will readily attack our electrophilic carbonyl carbon. From here, we make a tetrahedral intermediate. From here, we're going to kick out our leaving group, and chloride is a wonderful leaving group. From here, we get our corresponding aldehyde, and that aldehyde can be attacked with a second equivalent of hydride, and that in turn gives us our primary alkoxide ion. And if we add any acid during the quench, we can quench this alkoxide ion and generate a neutral isolable primary alcohol. So the student proposed mechanism for this reaction was completely reasonable. Any questions on this reaction? Any questions I can address before we move on? Well, if you have an acidic species well, we're not assuming acidity. The last comment is just if you quench the reaction in a later step, that's how you get the isolable alcohol. At the end of this mechanism, at the end of this first line as drawn, we just get the alkoxide ion. I'm just saying commonly you just isolate the alcohol after an acidic quench. And we can do many other things with the alkoxide ion. We can alkylate it, we can acetylate it. It's still a nucleophilic species that we can further react in solution. Commonly though, you just quench with acid and that gives you the alcohol. Did that answer your question? Yes, yeah. The quench for these aluminum hydrogens are usually slightly annoying in practice just because the aluminum complex and this like cake of aluminum has to be, you have to wash your product off from the aluminum, and there are usually detailed workups for that. Anyway, let's keep going then, and let's look at another example. This time we have an acetyl chloride. In this case, we have an acyl chloride starting material, and we're treating it with ethyl magnesium bromide, a Grignard reagent. So let's try to apply what we've learned earlier on in this chapter, and let's try to predict the product from this reaction and draw a mechanism for this reaction. So let's take about 3 to 4 minutes and work through this example. And I'd like students to share their in the chat verbally. You can also share photos of your work in the chat or annotated directly onto the class whiteboard. So as we work through this example, does anyone have any questions that I can address? Would anyone like to try to share their proposed mechanism for this reaction? If not, let's keep working through this example. So we have a student starting to annotate their proposed mechanism.
Sorry, I can't.
And I'll comment.
Double
Oh,
lines.
no worries. No worries. If anyone would like to, you can also share a photo of your work in the chat, and I'd be happy to annotate that for the class. Whatever would work. And there's plenty of space on the class whiteboard. So if anyone would like to try annotating their proposed mechanism, don't be shy to give it an attempt, and I'd be happy to provide input and feedback for any proposed mechanisms. So let's keep working through this example. And if you have any proposed mechanisms or proposed responses for this problem, don't be shy to share them in the chat, verbally, or annotated on the class whiteboard. And if there are any questions that I can address to help advance our discussion, don't be shy to ask them, and I'd be happy to address them. So we have our Grignard reagent, which is a strong nucleophile. We have the electrophilic carbonyl carbon. So our nucleophilic Grignard reagent will attack the electrophilic carbonyl carbon, and we would get a tetrahedral intermediate. From here, we can kick out our leaving group, which in this case is chloride. And that regenerates our carbonyl and gives us a ketone. However, that ketone will not stick around for very long, and that ketone will readily react with a second equivalent of Grignard, and that in turn gives us a tertiary alcohol. From here, we can isolate the tertiary alcohol after quenching the alkoxide ion with an acid. Yep, this student proposed mechanism looks completely reasonable. So let me just clear the student annotations and redraw this mechanism as part of our instructor key. So this acetyl chloride is quite reactive, or this acyl chloride is quite reactive. So common nucleophiles such as Grignard reagents will attack the electrophilic carbonyl carbon. That in turn generates a tetrahedral intermediate, which collapses and kicks out our leaving group, which is chloride. From here, although we generate a ketone in the first reaction with our first equivalent of Grignard reagent, this ketone does not stick around for very long, and it reacts with a second equivalent of Grignard via 1,2 addition to give a alkoxide ion. From here, we can quench this alkoxide ion with an equivalent of acid, and that gives us our neutral isolable tertiary alcohol. Any questions on this example and any questions on this mechanism for the reaction of acyl chlorides with Grignard reagents? Any questions on this example before we move on? Okay, so let's keep going and let's talk about a unique method to prepare ketones directly from acid chlorides. So reaction of an acid chloride or acyl chloride with a lithium diorganocopper species or a Gilman reagent yields the corresponding ketone. The reason why this reaction works is first, your organocopper reagent adds into the carbonyl. We have a textbook carbonyl substitution, and then we see a reductive elimination to generate our ketone. Because we go through this acyl diorganocopper species, and because the organocuprate reagents are milder, generally less nucleophilic species, we're able to get chemoselectivity for addition and attack onto the acid chloride without further reaction of our ketone. So this is a useful method to prepare ketones directly from the corresponding acid chloride. This transformation can also be accomplished with an organocerium reagent, though those are less common. So just to redraw this mechanism for our reference, first our organocuprate reagent will attack and add in to the electrophilic carbonyl carbon. From here, we'll then kick out our leaving group, which is chloride. Now, from here, this acyl diorganocopper species will then undergo reductive elimination, where we form a bond between this alkyl group and our carbonyl carbon, and we lose our alkyl copper species. That in turn gives us our corresponding ketone quite cleanly. The only downside is that making the organocuprate reagent usually requires multiple equivalents of organolithium or Grignard reagents to prepare the organocopper or organocuprate reagent. Any questions on this example? Generally, the organocuprate reagent is symmetrical, because generally you're trying to prepare a ketone with a defined alkyl group substituted. Did that answer your question? Perfect, perfect. So let's keep going then. And let's try to apply what we've learned to the following example. So in this case, we have this cyclopentanoic So we have this cyclopentane carboxylate derived acyl chloride, and we're reacting it with lithium dimethyl cuprate. What products would we observe, and what is the mechanism for this reaction? So let's work on this example for about 3 to 4 minutes, and let's try to predict the product from this reaction and draw the mechanism for this reaction. And if there are any questions, I'd be happy to address any questions asked in the chat or verbally. And I'd appreciate if students would share their responses in the chat, verbally, or annotated directly onto the class whiteboard. The lithium is just a counter cation. Looking at our previous example, in this case, the methyl groups are the alkyl groups are the alkyl groups on the organocuprate reagent. So we have a student beginning to annotate the mechanism. So in this case, we have an electrophilic carbonyl carbon on our acyl chloride. Our nucleophilic organocuprate reagent will attack the carbonyl carbon. And then we see collapse of this tetrahedral intermediate to make an acyl diorganocopper species. From here, we'll then see reductive elimination to generate our desired methyl ketone, as well as an organocopper reagent.
What would the other one be? Would it just be with two methyls on it, or?
Just one, because we've in reductive elimination, one of our methyls was incorporated to make the methyl ketone. So it's just a neutral alkyl copper species.
Okay.
Does that make sense?
Yeah.
Perfect. So the student proposal looks completely reasonable. So let me just clear those annotations and let's redraw the mechanism for this reaction. So in this case, we have our acyl chloride and we have our highly reactive dimethyl cuprate, organocuprate reagent. Organocuprate reagents are considered milder soft nucleophiles. And even with that in mind, they're still sufficiently nucleophilic to attack the electrophilic carbonyl of our acyl chloride. From here, we'll generate a tetrahedral intermediate. And we'll kick out our leaving group. And that makes our acyl dialkyl copper species, which undergoes reductive elimination to generate our desired methyl ketone in this case. And this alkyl copper byproduct. Does this mechanism make sense to everyone? Any questions on this problem before we move on? Any questions on this mechanism before we move on? Does this make sense to everyone so far? Any questions I can help answer? Okay, perfect, perfect. So let's talk a little bit now about the chemistry of acid anhydride. This is going to be almost a repeat of our discussion of acid chlorides. So we can prepare anhydrides via dehydration of the corresponding acid under high temperature conditions. This is known as pyrolysis. Not easily practical in most cases due to the high temperatures required. An alternative method to prepare anhydrides, especially if you're aiming to prepare asymmetrical anhydrides, is via reaction with a carboxylate salt with an acid chloride. This is a textbook carbonyl substitution reaction in which we replace our wonderful leaving group chloride with our nucleophilic carboxylate species. So in this case, we're dealing with acetate ion. So our nucleophile will attack the electrophilic carbonyl carbon. We generate a tetrahedral intermediate. And from here, we kick out our leaving group, and that gives us our desired asymmetrical anhydride. Does this mechanism make sense to everyone? Does everyone see how we can prepare asymmetrical anhydrides? Perfect, perfect. Okay, so let's try to apply what we've learned here, and let's try to propose a synthesis of the following anhydride. So what starting materials and reagents would we use to make the following asymmetrical anhydride? So let's take about 3 to 4 minutes to work through this example, and then I'd like students to share their responses in the chat. You can also share a photo of your written work in the chat, verbally, or annotated directly onto the class whiteboard. And if there are any questions, again, don't be shy to ask in the chat or verbally. So let's work through this example for a little bit, and let's try to apply what we've learned, and let's try to propose a reasonable and efficient synthesis of the following asymmetrical anhydride. So, does anyone have a proposal that they'd like to share with the class on the class whiteboard? So we have this asymmetrical anhydride, and we previously discussed methods to prepare anhydrides. So what starting materials would we use, and what conditions would we need? So the student decided to break the following bond. I'll call bond A. So in this case, we have the corresponding cyclohexane carboxylate derived acyl chloride and sodium acetate. Yeah, that's a perfectly reasonable synthetic route. Does anyone have another proposal that they'd like to share? Is there another proposal for how to prepare this anhydride? Does anyone have another proposal? Suppose we didn't want to use sodium acetate. At high temperatures, pyrolysis generally gives the symmetrical anhydride. And since we have an asymmetrical anhydride, it wouldn't quite be the best fit. You can also break the other anhydride carbon-oxygen bond, and you can trace this back to the corresponding carboxylate ion and acetyl chloride. That's also a viable path. Okay, so these student responses look great. So let's just highlight the retrosynthetic thought process here. So we can either break either of these bonds and trace back this anhydride to the corresponding acyl chloride and a carboxylate ion. In the forward sense for route A, we take this acyl chloride and just directly react it with sodium acetate. And that would give us our desired product. For route B, we take this carboxylate salt and react it with acetyl chloride. And that would also give our desired product. Does this idea in terms of how to prepare and synthesize asymmetrical anhydrides make sense to everyone? Any question example before we move on? Perfect. So let's keep going now. And let's try to apply what we've learned, and let's try to propose a synthesis of the following compound. And even though there are two routes in this case, one of the routes is slightly preferred. So again, we're tasked with preparing an asymmetrical anhydride, and using what we've learned from the previous examples, let's try to propose a synthesis for these asymmetrical anhydrides. So let's work on this example for about 3 to 4 minutes, and then I'd like students to share their proposed responses in the chat, verbally, or annotated directly onto the class whiteboard. And if there are any questions I can address as we work through these examples, don't be shy to ask in the chat or verbally. So we already have students starting to draw out and propose a synthesis of this asymmetrical anhydride. So in this case, the student is breaking the following carbon-oxygen bond that I'll label bond A, and tracing this back to propionyl chloride and a carboxylate salt. Okay, that proposed route is perfectly reasonable. Is there another route? Is there another synthesis of this compound that we can propose? Is there another synthetic route for this anhydride that someone else would like to share on the class whiteboard? So, is there another way that we can prepare this compound? Well, we can just break bond B and generate another acyl chloride and carboxylate salt. Yep, these two routes are the most logical routes to prepare the following asymmetrical anhydride. Okay, so let's clear annotations and let's discuss this. So for route A, we're breaking bond A to give propionyl chloride and a carboxylate salt. For route B, we're breaking bond B. And again, we can prepare asymmetrical anhydrides via the reaction of a carboxylate salt with an acyl chloride derivative. Does this example make sense to everyone? Any questions?
Which one would be better?
So if we think about it, generally it's more difficult to attack highly hindered electrophilic sites. So I'd say route A is slightly preferred.
Okay, that's why I drew that one first. That's what I was thinking.
Though both with enough forcing and higher temperatures could be accomplished. You can use other halides, though acyl chlorides are generally the easiest to prepare because thionyl chloride generates the acyl chloride from the corresponding carboxylic acid. Did that answer your question? Perfect, perfect. Okay, so let's keep going then. And let's talk about some common reactions of acid anhydrides. So just like acyl chlorides, acid anhydrides can be derivatized to carboxylic acids, they can be subjected to alkoholysis to prepare esters, they can be subjected to aminolysis to prepare amides, and they can be reduced to prepare aldehydes and alcohols. So the acid anhydride is a readily derivatized functional group. Okay, so let's keep going then, and let's talk about the first major reaction of anhydrides, which is the reaction with alcohols to generate esters. So a common anhydride used in reactions known as acetylation is acetic anhydride. So acetic anhydride can form esters from the corresponding alcohols and can form amides from the corresponding amines. In this case, our nucleophilic alcohol will attack the electrophilic anhydride carbon, and this results in a carbonyl substitution reaction. The same holds true for amides, which can attack the electrophilic carbonyl carbon of your anhydride and result in a carbonyl substitution reaction to prepare the corresponding amide. Let's draw the full mechanism for these two reactions below. So in the first case, if you have an alcohol and your anhydride, your alcohol attacks the anhydride carbonyl carbon, and we get a tetrahedral intermediate. From here, we'll kick out our leaving group, which is the wonderful acetate ion. Finally, as a last cleanup step, we'll pull off a proton from the ester oxygen. So as you can see, just like with acyl chlorides, we can prepare esters from alcohols and anhydrides. Does this mechanism make sense to everyone? It's functionally identical to the alkoholysis mechanism for acyl chlorides. Does someone have a question that I can address? Any questions I can address on this mechanism? Okay, let's look at the aminolysis mechanism next. It's functionally identical. So in this case, our nucleophilic amine attacks the electrophilic anhydride carbonyl carbon. We've seen this exact reaction and this exact mechanism in the acetanilide synthesis lab that we saw earlier this semester. Okay, so once we have a tetrahedral intermediate, again, we're going to kick out our leaving group, which is the acetate ion. And then as a last cleanup step, our base, which in many cases is going to be the acetate ion, is going to pull off a proton. That in turn generates our neutral isolable amide product. Do these two mechanisms make sense to everyone? Any questions on these reactions? Okay, so let's keep going and let's try to apply what we've learned to the following example. In this case, we have an asymmetrical anhydride reacting with propylamine in the presence of the basic triethylamine, which is just serving to pull off and neutralize any acid generated over the course of the reaction. So let's work on this example for a few minutes, and then I'd like students to share their proposed responses in the chat, verbally, or annotated directly onto the class whiteboard. And of course, if there are any questions as we work through these examples, don't be shy to ask them in the chat or verbally. So in this problem, we have an anhydride and a nucleophilic amine. Let's try to predict the product from this reaction and draw a mechanism for this reaction. So as we work through this example, would anyone like to share their proposed mechanism or predicted product for this reaction? Are there any questions I can address as we work through this example? Would anyone like to share their proposed mechanism on the class whiteboard? So we have our nucleophilic amine and we have this electrophilic anhydride. So what will happen from here? Yep, our nucleophilic amine will attack the electrophilic anhydride carbonyl carbon. From here, we generate a tetrahedral intermediate, which collapses. And that gives us our corresponding amide product. As a cleanup step, we're going to pull off a proton with triethylamine to get our neutral isolable amide product. Perfect. Yep, the student proposed mechanism looks completely reasonable. So let's just re-annotate it for our reference. So for asymmetrical anhydrides, you can attack it either anhydride carbonyl carbon with a slight preference for the less hindered position. In this case, our nucleophile, which is propylamine, will attack the electrophilic carbonyl carbon, and this will generate a tetrahedral intermediate. Generally, the acetate ion is a wonderful leaving group, and carboxylate ions as well are also great leaving groups in carbonyl substitution reactions. So when this tetrahedral intermediate collapses, we'll kick out our carboxylate leaving group, and that leaves us with our protonated amide product. From here, our base will pull off a proton. In this case, triethylamine is the most reasonable base in solution, given the reaction conditions. So we'll pull off a proton to isolate our neutral amide product. Does this make sense to everyone?
I thought that the
Oh, I see what happened. I see.
acetate ion leaves.
Sorry about that. I got mixed up with attack at the other position. Yeah. So in this case, re-annotating the student drawn mechanism, since we're attacking at the less hindered position, we get the following propylamine derived amide, and then triethylamine pulls off our proton. Yeah, and that gives us our amide product. Let's show the other potential product that we would get, which occurs with the attack at the more hindered position. So in this case, propylamine will attack the more hindered position. We make a tetrahedral intermediate. And then from here, we kick out our leaving group, which is the acetate ion. That in turn gives us our amide product, which is isolated as the neutral amide after deprotonation with triethylamine. So in this case, because we have an asymmetrical anhydride, we get two amide products. Does this example and do these mechanisms make sense to everyone? Sure. Any other questions on this example? Attack at the least hindered position is preferred. So acetylation of your propylamine nucleophile is preferred over the attack at the more hindered position, just because the methyl group exerts less steric hindrance than the bulky cyclohexyl group.
Sorry.
Yes, please go ahead.
I was just gonna ask about in the diagram in the previous page, the formation of acetaminophen. Why does it prefer to attack the nitrogen and not the alcohol? Because we learned the mechanism for both.
So looking all the way in the previous, yes. So if we compare an alcohol and an amine, in the neutral form, which of these species has the more nucleophilic lone pair?
More nucleophilic. The nitrogen?
Yep. So the amine generally is
Okay.
more nucleophilic under neutral conditions, and that's why it preferentially reacts with acetic anhydride.
Okay.
The same reason why, for example, in salicylic acid, the alcohol reacts preferentially over the carboxylic acid.
Oh, okay.
Does
Yeah, that makes sense.
logic make sense? Perfect.
Yeah, thank you.
Any other questions on this example? So we've looked at alcoholysis and aminolysis of anhydrides to prepare esters and amines. Any other questions on this example?
Sorry, I don't know if you touched up on this. So for the first example, the cyclohexane portion, it just gets cut off.
Yes, so we lose, so when this tetrahedral intermediate collapses, we lose this cyclohexane carboxylate species. So we're generating as a byproduct this carboxylate ion.
Oh, okay.
Does that make sense?
Yeah, thank you.
Perfect. Any other questions on this example? So we're at a good stopping point for today. So what we'll do is we'll archive this recording.